Let's now go to the roof beam. So I'll go to view and then activate level 3 so that we can see the roof beams. We may deactivate the supports so that we will have a clearer view. So this is my logic class. Now this is just for activity purposes, and this is not really or entirely applicable to the actual scenario. No, this is just to simplify. Now I have noticed in my own observation that the loads on the roof beams or the sizes of the roof beams are somewhat half, no, in capacity of the sizes in the normal floor beams, the regular floor beams. So therefore, my conclusion is the load that you are going to place on the roof beams will be half of the load that you are going to place in the normal, no, the normal beams, the beams with the slab. So with that, I will be using the slab method of loading, but I will load only half. Meaning to say, for dead load, I will load only 0.25 superimposed dead load, and for live load, I will load, now if you can see here, for the live load, the load is say 1.9. I will divide that load into 2, and I will load that to the roof beams. Alright, so I hope that is clear. So I now go to loads and then create. Make sure that you are in the dead load first, then create, and the slab thickness is still the same, half of the thickness, because you are trying to get half, half of the value of the load. So half of 125, that will be 62.5. So just round it off, or roughly round it off to 65 mm. Although there is no slab, but since we are trying to simulate a load which is half of the normal floor, so we place here 65 mm, and then the pressure here will be 0.25. Okay, so let's try to where was that? Okay, yeah, first we have to create a slab with conventional values. 0.25 and then 65. Okay, anyway, we can edit this one later. So what frame C is trying to do is you have to assign the slab first before you can edit. Alright, so after that, you can now edit, select all the slabs, remember the roof area doesn't have a slab, but we are just doing this because we are trying to simulate a slab load, or a load which is half of the load of the second floor, because we're trying to assume that the roof beams will have half of the capacity of the second floor beams. So slab thickness is 65 and the pressure is 0.25. Alright, so let's now go to live loads. Click edit, then select all the slabs. And then the pressure, instead of 1.9, we divide 1.9 by 2. So 1.9 divided by 2, that will be 0.95. So we place here 0.95 kilonewtons per square meter rather. Alright, so we have just loaded the second floor or the roof beam in the assumption that the load is half of the load of the second floor slab. Alright, so this is already the complete set of loadings that we load to our structure. By the way, I have not loaded the partition load for the second floor because there is a code provision that if your load is more than 4.8 kilopascals, you can neglect loading the partition loads. But again, this is still up to you as a designer if you want to use that assumption or not. So if you want to be conservative, you can load the sides with partition loads. Okay, but as far as this activity is concerned, our loads are already complete. Next, we go to load combinations. Now for load combinations, because it's not given, we will use the USD load combinations, which is first is dead load plus live load, then 1.2 dead load plus 1.6 live load. There are also earthquake load combinations, but we will not use that because we are not given the earthquake parameters. So create load cases. So far we have two loads, the dead load and the live load. So we will add a load case. This is a load combination. Dead load has a factor of 1 and live load has a factor of 1 again. And then the load case is DL. You have to really name this load case DL plus LL. Next, another load case will be 1.2 DL plus 1.6 LL. So 1.2 and then 1.6. Then click add. Click exit. With that, you now have two load combinations. You can see it here. Dead load, live load, DL plus LL, and 1.2 DL plus 1.6 LL. At this point, we are now ready to perform analysis. By clicking this button, we can start running our analysis. And in a few seconds, we can generate all the results. Alright, so linear analysis is complete and we are directed to this ribbon wherein we can see the results in terms of displacement, in terms of shear, in terms of moment, in terms of reaction forces and axial forces, and we can export our results to spreadsheets. We can also increase or decrease the graphic scale, and we can show the maximum values or the elements with the maximum values. So let me start with the moment diagram. For the major axis, let's try to view the moment. Alright, so this is the moment diagram in terms of color-coded values. And this is the legend. So 63.37 is in this portion here, which is very logical. Now we have here a positive moment because it carries the slab. Positive moment meaning the elastic curve is somewhat smiling, the elastic curve of the beam. So we have positive 63.637. And we have negative moments, the blue one, negative 84.58. So let's look for that moment value. This one, the dark blue here, which is also very logical. The moment there are always negative because they are near to the support and the tension side is on the upper side of the beam. So negative 84. Alright, so that is how to model and generate results for a 2-story classroom and modeling it in 3D.